Welcome back. Problem 5.103. This problem is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer and Johnston, 6th edition. And the topic is singularity function or Macaulay's method. So statement of the problem is in part A, we have been asked using singularity functions, write the equation defining the shear and bending moment for the beam and loading shown. And in part B, use the equation obtained for M to determine the bending moment at point E and check your answer by drawing the free body diagram of the portion of the beam to the right of E. So you can see this is a simply supported beam having pin support at A and a roller support at D, and their distributed load from A to B having magnitude W naught, and from B to E having magnitude 2W naught, and then from E to D it is W naught. So what we will do is that we will find the equation of shear and bending moment by using singularity function. So let's start with our first solution of first part. So what if we remove this support at point A? So you will be having reaction force. Let this is represented as RA. And what if you remove this roller support at point D? So you will be having a reaction force, and this is equal to RD. And we will find this RA and RD by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see W naught which is acting over here, and when we convert this W naught into a point load, so it will be equal to W naught into the length over which it acts, which is A, and this will act at a distance of A by 2 from either E point or D point. So I will write A over 2. Now this W naught when converted into point load, so it will be equal to 2W naught into the over length over which it acts, which is 2A. So I will write 2A, and that will act at a distance of A from point E. Clear? And the last load, which is W naught, this one which when converted into point load, so it will be equal to W naught into A, and the distance this from point B, from mid till point B, is A by 2. Now you can see the distance from this point load and point A will be equal to 7A by 2. Why 7A by 2? Because you can see this is A plus A, and this is A, and this is A by 2. So it will give you 7A by 2. And now we will apply sum of all moment about point A is equal to 0. So starting from this load, RD into perpendicular distance is 4A about point A, and it is producing counterclockwise movement, so it will be positive. So I will write 4 times A multiply by this RD. Clear? And the second moment is due to this load W naught into A, and perpendicular distance is 7A by 2, and it is producing clockwise movement, so it will be negative. So I will write minus W naught into A into 7A over 2. The another moment of this load about point A is this load multiplied by perpendicular distance is 2, and this is also clockwise, so it will be negative. So I will write minus, this will be 4W naught into A into perpendicular distance is 2A. And the last force which is producing moment about point A is W naught into A, and perpendicular distance is A by 2, and this will be also clockwise. So I will write minus W naught into A divided by 2 is equal to 0. So we will get 4RD multiplied by A minus 7W naught A square over 2 minus AW naught A square, and this will be minus W naught A square over 2 is equal to 0. So it means that 4RD into A is equal to 7W naught A square over 2 plus 8W naught A square over 1 minus plus W naught A square over 2. So what if I take LCM? So this is 2. So this will be 7W naught A square plus 8W naught A square plus W naught A square, and that will give you 7 and 8 15 plus this is 16. 7 8 15 plus 16. 16 divided by 2 is 8. Okay, I think I have made mistake. Okay, this is 7 into W naught. Okay, this there is 1, so this will be 16 because 2 divided by 1 is 2 and 2 into 8 is 16. So made this correction. Now 16 and 7 is 23 plus 1 24. So correct it. This will be 24 W naught A square over 2, which is equal to 12 W naught A square, and that is equal to 4RD multiplied by A. So what we will get if you divide 4A on both sides, so you will get RD will be equal to 3W naught into A. So this is the reaction force of this roller support on the beam. Now we'll find this RA by using equation of equilibrium, that sum of all forces along y direction is equal to 0 and upward force is taken as positive. So we do not have R. So RA minus this W naught into A minus this 4 times W naught into A and this minus W naught into A plus this RD, which is plus 3W naught into A, is equal to 0. So you can see this will be minus 4 minus 1 minus 5 minus 6. So minus 6W naught into A plus 3W naught into A will give you RA will be equal to minus 3W naught into A is equal to 0. So from here you will get RA will be equal to 3W naught into A. So now we have reaction on both sides. So what we are doing is that we will represent it over here. So you can see this is 3W naught into A, and this is also 3W naught into A. Since we have distributed load on the beam, clear? So what we will do, go to this figure, and you can see you have distributed load that is acting at a distance of A. So shear force equation will be this one. But this distributed load is starting from this and it is going towards the end. And here you can see this is this portion and it is up to this portion and this portion. So we will make it as per our diagram. So what we will do is that if I make it as a horizontal, because all this will be W naught. So this will be your one load. So this now this remaining this portion will be also W naught. Clear? So we will cut it. This will be also W naught. And what if I make it toward this side? Clear? If I add this much load, W naught. So on lower side I will make the same but in above direction. Clear? This will be W naught in order to cancel effect. You can see this and this effect will cancel and we will only left with this same portion. Now we can apply this figure for finding the shear force and bending moment diagram. So first we will find V of X, shear force equation. Starting from left hand side and moving toward right hand side, we will neglect the last force, which is 3W naught into A, because you have seen that in previous problem I have shown that the effect of this force becomes 0 when X is less than 4A or equal to 4A. So you can try it yourself. So starting from this point load. So first load is this point load. This is the figure of point load that is acting downward. So shear force equation is this one. So for here, this load is upward. So it will be positive P. So P here is 3W naught into A and X minus A. A is equal to 0 because this load is starting from point A. So this is 0. Now the second load is this W naught, which is acting throughout the length. Clear? Let me show you. It is acting throughout the length. Clear? So we will use this equation, W minus W naught into X minus A. A is equal to 0 for this load. So I will write minus W naught into x power 1. Okay, the another load is this W naught which is acting. So I will write minus W naught into x minus. Now you can see this load is acting at a distance of a from this point A. So W naught into x minus a power 1. And the last load is this one which is upward. So this load you can see this is negative for the downward and this load is upward. So W naught will be positive. So I will write plus W naught into x minus. Now this load is acting at a distance of 3a from this point A. So I will write x minus 3a power 1. To further simplify it, this shear force equation will be equal to 3w naught a x power 0 is 1. So minus w naught x1 minus w naught into x minus a power 1 plus w naught into x minus 3a power 1. So this is your shear force equation. Now we'll find the bending moment equation. So for bending moment equation, m of x will be equal to, again starting from this left side for this 3 low point load. So bending moment equation is this one. Since this is downward force and this is negative, so for upward force it will be positive. So plus p, and p is 3w naught into a into x minus a. A is equal to 0 because it is starting from point A. So power 1. The second load is this W naught, clear, and we will write the W naught equation is this one. Okay, so that will be equal to minus 1 over 2 W naught into x minus a power 2, and a is this distance, clear. The third load is this W naught for the length of 3a. So I will write minus 1 over 2, let me correct it, minus 1 over 2 into W naught into x minus, x minus 3a, 3a power 2. We have left this one, okay, because for a here it is equal to 0. So minus 1 over 2 W naught into x square. Let me explain. The first term is for this, clear. This term is for this portion and this term is for this portion, and the fourth term is for this portion. Okay, now if you simplify this, so you will get this m of x will be equal to 3w naught ax. This term will be equal to minus 1 over 2 w naught x square. This term will be equal to minus 1 over 2 w naught into x minus a square plus, okay, for this load this is upward, so this will be plus. So plus 1 over 2 w naught into x minus 3a whole square, and this is, let's say, equation number 2. So this is the equation of shear force and this is the equation of bending moment for the beam and loading shown. So now our next part is that what use the equation obtained for m to determine bending moment at point E. So we have to find the bending moment at point E. So E is at a distance of 3a from point A. So we will put x is equal to 3a in equation 2. So when you put x is equal to 3a, so it will be equal to 3w naught a into 3a minus 1 over 2 w naught into 3a whole square minus 1 over 2 w naught into 3a minus a power square plus 1 over 2 w naught into 3a minus 3a whole square. So this term will become 0 and we will left with moment m of x will be equal to 9 w naught A square minus 9 by 2 W naught A square minus 1 over 2 W naught into 2A. 3A minus A is 2A, so 4A square. Okay, so if you take LCM, so it will be give you 2, so 9 W naught. Okay, 2 divided by 1 divided by 2 is 2, 2 into 9 is 18. So 18 W naught A square minus 9 W naught A square minus 4 W naught A square. So it will give us 9 and minus 4 is minus 13 plus 18 is 5 W naught A square over 2. This is moment about point E. So I will write moment about point E will be equal to 5 W naught A square over 2. And this is the answer of our second part. Now in third part we have been asked to check your answer by drawing the free body diagram of the portion of the beam to the right of E. So to the right of E, if you take this section and draw the free body diagram, you will get this moment ME and we will compare it. So what we will do is that we will section it over here and draw the free body diagram. So let me move toward this page. So this is the beam. Okay, this is your point D where you have 3 W naught into A and there is a distributed load acting on it which is equal to W naught. This length is A. Clear? So when you cut it, you will be having a shear force V. This is point E, so it will be VE and you will be having a moment ME. So we'll find this moment by using equation of equilibrium, that sum of all moment about point E is equal to 0, taking the counterclockwise moment as positive. So when this W naught load is converted into point load, it will be W naught into A and that will act at a distance of A by 2 from either side. Now you can apply the equation. So about point E, one moment is ME, which is clockwise. So I will write minus ME. The second moment is due to this load into perpendicular distance is A by 2 and this is also clockwise. So it will be, okay, this will be clockwise. So it will be also negative. So I will write minus W naught into A divided by 2. And the another load which is producing moment about point E is this load into perpendicular distance A and this is producing counterclockwise movement. So it will be positive. So I will write plus 3 W naught A into A is equal to 0. So moment about point E will be equal to minus W naught A square over 2 plus 3 W naught A square. So if you take the LCM, so it will be minus W naught A square plus 6 W naught A square will be moment about point E. So moment about point E will be equal to 5 W naught A square over 2. And you can see that this is the moment by cutting the beam and taking the right side of point E. Now you can compare it with this value that is obtained from the equation of bending moment. Both are same. It means that our required equation of shear force and bending moment is correct. So this was all about problem 5.103. I hope you have enjoyed this video and you have learned from this. Those who are new to my channel, then subscribe it and don't forget to press icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.